We're going to pick up where we left off. We've been talking about the qualitative perspective on Bronsted-Lowry acidity of organic compounds. Remember, to compare acids qualitatively, we need to look at the conjugate base of each acid. So Bronsted-Lowry acid is one that donates a proton, resulting in a conjugate base. If the conjugate base, A-, is very stable, in other words, a weak base, then the acid must be a strong acid. This is useful because we can just look at the structure of compounds and not have to have their pKa values available. These are the factors we already talked about. Use the acronym ARIO to remember this. Atom, what atom is that proton on? If we have greater electronegativity when we're comparing atoms in the same period, the more electronegative atom will be the stronger acid because the base is more stable. If the atoms are in different groups, in different periods, but in the same group, we're going to look at their size. A larger size is going to stabilize that negative charge because the negative charge is distributed through a larger volume, and so the charge density is less. Resonance will stabilize the negative charge. If that negative charge is delocalized over several atoms, again, that decreases the charge density. There are inductive effects. If we have electron withdrawing groups such as chlorine anywhere near that negative charge, that will help to pull the charge density away and again stabilize the negative charge. The last one is orbitals, and we haven't talked about that one yet. That's the topic for today. If we look at a question like this, we understand why we need a fourth criteria to look at. Which of the two identified protons in the following compound is more acidic? So we're comparing this hydrogen and that hydrogen. First thing we need to do is draw the conjugate bases. So I've taken a shortcut here, make a little skeleton. So first we'll remove the one on the left. So I'll take off this hydrogen, and then what's left there? Do we just leave it like that? Is that the conjugate base? No, if we remove a proton, now we have a charge. There'll be a negative charge, and there will be a lone pair. That's the pair of electrons that were in the bond. They are still there. The proton left, that's just the hydrogen nucleus. So then over here, we're looking at the hydrogen at the other end. Remember, take him off. And what's left? A lone pair and a negative charge. So those are our two bases. If we compare the first three things, A, R, and I, atom, resonance, induction, we see there's no difference between these two. We need a fourth factor, and that fourth factor is orbitals. Because when we look at these, what's different? What's different about these two carbons? When they both have a lone pair and a negative charge, how about the bonds? Look at the bonds. What's different? This one has a carbon double bond. This one's got a triple bond. So we need to look at the bonds and at the orbitals and figure out what's going on here. So we need to review some stuff from Chem 1A. Atomic orbitals. Do you remember these guys, these funky shapes? These are atomic orbitals. Orbitals are regions of space that can be occupied by electrons. The s orbitals are spherical. The p orbitals are these, funky kind of dumbbell shapes. We learned from quantum mechanics that electrons, although they are particles, they also behave like waves. So we have to figure that in. These orbitals have phases just like waves have phases. What's a phase? Well, here's a drawing of a sine wave. And imagine this is a wave on a lake. We can visualize that a little better. Here's the average level of the lake. Half of the time the wave is above the level of the lake, and half the time it's below. So the phase above and the phase below. You can call them plus and minus. I prefer to think of them as opposite phases because it does not mean that one side's positive and one side's negatively charged. We can get confused about that. So in these drawings, The reason one side's red and one side's blue is because the p orbital has one lobe is one phase and the other lobe is the other phase. S orbitals are not like that. They're going to be one phase or the other at any given time. So what do waves do? And this falls under the category of valence bond theory. There were multiple theories of bonding, and this is the one that explains what we're trying to figure out right now. Waves can interfere constructively or destructively. If we have two waves coming together and they are in phase, they will add together, and we call that constructive interference. The wave gets bigger. They reinforce each other. If we have two waves that are out of phase and we bring those together, they cancel each other out. This is called destructive interference. The waves will get smaller, or they can possibly even disappear. According to valence bond theory, a bond is the sharing of electron density between two atoms as a result of the constructive interference of their atomic orbitals. So here we have two hydrogen atoms, their s orbitals interact in a constructive way, and we get a covalent bond. Now, it's important to know that the orbitals in a molecule are not necessarily the same as the orbitals in the atom by itself. Hybridization is just a mathematical procedure in which we take those standard atomic orbitals and combine them to form hybrid orbitals. We can think of this as adding them together or averaging them. We're combining them. A couple things to remember: the number of hybrid orbitals is always equal to the number of atomic orbitals that were put together. The type of hybrid will vary with the type of atomic orbitals that you mix, and the shape and orientation, blah, blah, blah. Okay, so let's look at the most simple case where we're combining an s orbital and one p orbital. So here are the atomic orbitals. When we hybridize them, we get these two. We get two orbitals because we started with two orbitals. We're going to call these sp because they're the combination of an s and a p. So very clever name, sp, hybrid orbitals. Here's what they look like separately. Notice that we've got a small lobe on one end, and a large lobe on the other. Kind of looks like a turkey drumstick. We typically, though, show them together, and we just kind of ignore the smaller lobe. So how did this come about? We can kind of visualize it. Here's an s orbital, and here's the p orbital. Remember, the p orbital has phases. One side is one phase, and one side is the other phase. Having a little trouble drawing here. Okay, there we go. Kind of looks like a geek with lab glasses on, doesn't it? Well, these can combine. This is adding. And so when we add these two together, these parts over here that are in phase are going to add together. And so that part's going to get bigger. And this part over here that's out of phase will have some destructive interference, and that will get smaller. So you're beginning to see why I'm not an artist. Professional artist. Would not make a good living at that. So we can add them or we can subtract them. Subtracting is the same as adding a negative. So we can do that by just switching the phases of that p orbital. And so we can add them or we can subtract them. Now we have the constructive interference on the other side and the destructive interference. It's just flip-flopped. So that's kind of how you get those two orbitals from the s and the p. So these are the two sp orbitals, and they will be oriented in opposite directions. So the angle between them will be 180 degrees. And that's important. So in acetylene, we have sp hybridization. Here's an orbital diagram. And what happens is we get one s and one p orbital. They hybridize, they're averaged together, they become degenerate, the same in energy. And they will be between the s and the p level in energy. And we have these two that are not affected. So here in this illustration, the gray, this is one sp hybrid orbital, and here's another one. This one's overlapping with the hydrogen atom and making a sigma bond. The other one is overlapping with an sp hybrid orbital of the other carbon, also making a sigma bond. We're left with these two unhybridized p orbitals, and they just don't hang around half empty. They are also going to overlap. These two can overlap and form one pi bond, and these will overlap and form another pi bond, and that's how we end up with our triple bond there. sp2 hybrid orbitals, we're going to take the s and two p orbitals, and again we're going to get sort of this drumstick shape, but the orientation is different because there's three of them. So these are going to form a planar triangle, trigonal planar. This is what happens with ethylene. 1s and 2p form 3 sp2 hybrid orbitals. And this matches up with our observations of the geometry of ethylene. So we've got 3 equivalent degenerate orbitals arranged in a trigonal planar fashion. We have one unhybridized p orbital. This will overlap with the unhybridized p orbital on the other carbon, forming our double bond. sp3, same idea, 1s, 3 p's. Now we get 4 orbitals because we started with 4, and these are going to make a tetrahedron. This is what happens in methane. So let's look at this. It's important to be able to identify the hybridization of the carbons. So let's look at this guy right here. And we're going to look at how many groups are attached. We've got the hydrogen and the carbon. That's 3, right? We need 3 orbitals. Well, if we write sp3, spppp on our fingers, and just count up the number of groups. I need 3, so sp2. So this guy is going to be sp2 hybridized. We're running short on time, so I'm not going to do all of them. We're just going to do the ones we're interested in. What's this guy? He's got 2 things, a carbon and a hydrogen, sp. So this is sp hybridized. How does this affect acidity? Well, orbitals that have more s character are going to be shorter, and they're going to hold the electrons closer to the nucleus. The s orbital is round, spherical, and the p orbitals are long and skinny. So here we've got 50-50 s and p. It's going to have more of an s shape than the other 2 hybrid orbitals. So more s character, shorter orbital. The sp3 is going to have the longest, and we can see evidence of this when we look at the bond lengths of the carbon-hydrogen bonds in 2 carbon molecules. We see that the longest bond, 109.4 picometers, comes with the sp3 hybridization, 106 for the sp. So there's some evidence of what we're talking about here. And this amounts to different electronegativities for carbon atoms. It's going to depend on the hybridization, because electronegativity is the ability of an atom to attract electrons. Well, an sp hybridized carbon is going to have the electrons closer to the nucleus. That's attracting electrons. So an sp hybridized carbon is higher in electronegativity than an sp2 and then an sp3. And so electronegativity of the atom was our first factor. Right? So you can see that this is going to affect. So back to the original question, which of these is more stable? Now we're looking at these carbons. This one is sp2, right? Hydrogen, this is where the other hydrogen was, the lone pair. The lone pair counts as a group. Lone pair, so this is sp2, this one's sp, I almost said sp3. Which one's shorter? This one. So this guy on the right is the more stable base, and so the hydrogen on that carbon is more acidic. So, summary, other factors being equal, the acidity will vary with the hybridization of the atom. The most acidic will be the sp, the least will be the sp3. We can compare pKa's for these 2 carbon molecules, and we see that acetylene is definitely much more acidic than ethylene, a pKa of 25 versus 44. Here's an example. Let's identify the more stable anion and explain. What are we looking for? Atom, resonance, induction, all the same. We're looking at orbitals. What's the hybridization of this carbon atom? There's the lone pair and 3 carbons. That's 4 groups. 4 groups, sp3, right? That's sp3 hybridized. What about this carbon over here? Well, that one's sp2. Sorry, sp. I keep saying that. sp. Which one's more stable? The one that is more electronegative, the one that holds the electrons closer, the one with more s character. This guy. Because the electrons are held more closely to the carbon atom, which is a more stable situation.